So we are following on from the pKw and strong base calculations. We're looking at adding some strong acid to strong base, and then we're going to look at some weak acids. So calculating the pH. I think this is relatively simple, but I think people panic about these questions. These questions, you really need to go back to what you learned at year 12. And the key equation is C equals N over V. Now, as long as you remember to use that equation, you're going to be pretty much okay on doing this. So, I'm going to calculate the pH of a solution formed when 50 centimetres cubed of 0.1 molar H2SO4 is added to 25 centimetres cubed of 0.15 molar NaOH. Let's make this a little bit smaller. So, first thing you need to know is to know the number of moles of H+. So, remembering that N equals C times V. Your moles of H+, let's put this on this side of H+. We've got 0.1 molar times 0.05, which equals 0.005 moles of H2SO4. Therefore, your moles of H+, because it's a diprotic acid, is 0.01. Okay, so let's have a look at the OH minus then. Same thing again. Okay, so N equals C times V. So you've got 0.15 times 0.025, which equals 0.00375 moles of OH minus. Right, so you've worked out the amount of moles of OH minus and H plus. Now what you can see, okay, you want a one-to-one relationship obviously for these, because we've already accounted for the fact that it's a diprotic acid. Okay, but we're actually just looking at this part in this equation now. Yep. So they're one-to-one relationship. So we have got more H plus than we've got OH minus. Okay, so our excess H plus is going to be 0.01 minus 0.00375, which equals 0.00625. And then you need to just work out, right, you need to work the pH out. The thing that people always forget to do, 50 centimetres cubed plus 25 centimetres cubed. So this is the number of moles now. Let's change colour. So you see equals N over V. Now on N is 0.00625 divided by 0.075. Okay, because we have 25 centimetres cubed plus 50 centimetres cubed. So that comes out at 0.0833. If you take the negative log of that, your pH, I can work this out, sorry it's looking very messy now, is going to be 1.08. So now that we've been able to work out strong acids and strong bases added together, you should be able to do those calculations. We're focusing in on the Ka for weak acids. We're going to link Ka to concentration and pH, and we're going to convert them. Okay. So what you'll remember from GCSE was that a weak acid was something like ethanoic acid, and the reason why it was weak was because let's have CH3COOH. You'll remember that it is only partially dissociated into its ions. Okay, so because it's got a reversible reaction here, not all of it will dissociate into H plus and CH3COO minus now. So we make a general equation now to help us work some of this through. So what we say is that HA, where this is the weak acid, is HA because H plus is part of any acid. Okay, so it dissociates into H plus plus A minus. Okay, in this case, A minus, let's say, is CH3COO minus, but it can be anything. So we now know how to write an equilibrium for this. Okay, and we have defined now a Ka. Okay, so it's an equilibrium constant that refers to the acid equilibrium. And just like any other equilibrium constant, so I'm leaving out my state symbols being very naughty here. Okay, obviously we need some AQs in there. Right, it's going to Ka is going to be H plus concentration multiplied by A minus concentration divided by the HA concentration, and you can work the units out for this. Okay, it's going to be moles decimeter to the -3, because you've got twice at the top and once at the bottom, so they'll cancel out. So we talked in the last video about pH and pOH. Okay, and I showed you that pH plus pOH was equal to the pKw. Okay, that was your cheeky check for pHs of bases. But we can also define now for the Ka, you can define a pKa. So pKa is minus the log of Ka. Okay, so what is this actually telling us? So Ka is H plus, oops, that's what happened to my pen there, A minus over HA. Okay, now because of the way that the logs work, I have to think carefully about this. So if the Ka is less than 1, then the acid is weak. Okay, so what it's telling you is that this number up here is lower than this. Okay, whereas if the Ka is greater than 1, means that the Ka is actually not a fraction, it's a big number, and that it's more dissociated, so there's more H plus and A minus and less HA. Right, so obviously so far we learnt that pH equals minus log of the H plus concentration. Okay, which is all fine and dandy for HCl, let's say, where we know that it all goes to H plus and Cl minus. Okay, so we know that if we've got 0.1 molar HCl, we're going to have 0.1 moles of H plus. But unfortunately for an ethanoic acid or any other weak acid, we are not sure how much of it's dissociated. We need to use the equilibrium constant to find that out next. So this should actually look relatively familiar to you, because this should now remind you of the equilibrium section that we did in year 12 and we recapped again in year 13. So we're taking a general equation, HA going to H plus and A minus, okay, and we're saying that when we first have the HA before it's dissociated, we've got this much, and we've got 0 H plus and 0 A minus, but after dissociation you've lost X amount, okay, and it's gone to produce H plus and A minus. So here's the next big assumption that we have to make to now work through our pH for weak acid. And I know that last year's group didn't like this very much at first, but they kind of came to accept it eventually. Because it's a weak acid, very few molecules of HA are dissociating to give H plus and A minus. Okay, so we make an assumption that HA is equal to HA minus X. So we make an assumption that X is very small. So if X is very small, we can ignore. So we ignore it. Okay, so that simplifies that previous expression down to Ka equals H plus concentration to OH minus A minus concentration divided by HA. But of course, we also know that these are equal to each other. Okay, so the H plus has to be equal to the A minus concentration. So you can then simplify this right down to Ka equals H plus squared over HA. At this point, it's relatively simple to rearrange it and then find the pH. Okay, so you just need to take a square root and rearrange the equation, and then you can work out your pH. This is just a slide with a little summary that may help you. These are the key bits to remember. I think obviously this bit is straightforward, the first bit, that you've got to remember these assumptions, and then the rest of it all just falls out. So I can do a little example here. So these are relatively straightforward calculations, then it gets a little bit harder later on when we do buffers. Okay, so the first thing we want to write is that our Ka is going to be our H plus A minus over HA minus X. Okay, and remember we said that Ka equals H plus squared over HA. Now, we've got our Ka, been given that, 1.74 times 10 to the minus 5. We've given our 0.1 molar concentration of HA. Just going to make this a little bit smaller. Okay. So we've got 1.74 times 10 to the minus 5 is going to be my H plus concentration squared divided by my 0.1. So I need to take this 0.1 up here. Then I need to take the square root, and I'm just going to pull up the number because I'm not going to be able to do that one in my head. I need to find the answer for you quickly. Where is it? Okay, so my H plus concentration from this, I'm reliably informed from my previous work, is 1.32 times 10 to the minus 3. I just need to take the pH, so minus log the H plus concentration. Again, I'm going to look up the answer because I can't find it, and it's 2.88.